Okay, so like I mentioned, we are about to start the class called Lines of Best Fit. Let's give it a shot on page 59 here. In this lesson, we examine plots of real-life data and explore how to use the line of best fit. With apologies, this first example is rather morbid, but the data is accurate. In 1982, drunk drivers were responsible for 25,165 deaths in car accidents. That was 57.3% of all fatalities due to car accidents. Said another way, 57% of all the fatalities due to car accidents were due to drunk driving. The other, 43% of fatalities in car accidents were due to other reasons, not drunk driving. Here is a table showing the percentages of fatalities due to drunk driving for several years, starting in 1982, ending in 1999. Percent fatalities, alcohol related, 57%, 51%, 50, 47, 40, 38, and 37. What do you notice about those numbers in the right-hand column? They decline, right? We can say that just looking at the numbers. They are decreasing, but it's really kind of hard to say anything else just by looking at a table of values. It turns out you get a lot more information visually if you plot these points. And so that's what we're going to do down here. Or that's what I've done for you, I should say. So to display the data in the table, we're going to use something called a scatter plot, brand new word. It just means plot data points. We're going to let P represent the percentage of driving fatalities that were alcohol related at T years since 1980. So T equals 0 is 1980, T equals 2 is 1982. 1980 is our starting point, okay? And so in this example, there's the graph, percent fatalities on the vertical, year on the horizontal. Again, 1980 is our starting year here. Part A, label the coordinates of points A and B, and it says don't estimate for point B. It says use the table to get the exact coordinates. Okay, so point A, where's point A? Right here. All right, so point A, I guess we can just read off, right? What does that say? Is 8, 50? So that seems easy enough because it appears to be a nice point. Both coordinates are integer. But part B is kind of floating here in the middle, 19-ish, 37, 38. It's hard to know, but you have the table. The points came from the table. So this guy right here, being at 19, I think, really means what number in the table? 1999, that's right, because 1980 was our starting point, right? So this is 19 years from 1980. So according to the data in the table, what was the number going with 1999? 37, right. So I buy it, but if you said 38, I would have bought that too. So we got to read from the table. So this is 1937. Okay, part B. Does the scatter plot show any relationship, pattern, or trend between the two variables? That is, does the data appear to be increasing or decreasing or neither? So now that we've got the visual in front of us, we should get the same answer. Still decreasing, right? We can see this trend, but you can see more than that. You can see that it's not decreasing at a constant rate, because if it was, these lines would all lie perfectly on the same straight line. Yeah? These points would all be on the same straight line. So some years, going from like here over to here, I think that's 3 years in time, and we had maybe a 7% decline in the percent fatalities due to drunk driving. But then going from this point to this point, looks like another 3-year decline, but the percent fatalities didn't change by very much, right? Maybe they dropped to 1%. So we get more information from the table, from the graph, than from the table. Okay. Moving on to part C. On the scatter plot, sketch a line that you think, quote, fits the data the best. You're going to use a straight edge. You can use that folder on your table. You can use your calculator. Just find a straight edge. We are going to get different answers to this problem. You are just eyeballing here, and you are trying to draw your line of best fit. Graph itself. So let's just give you a little bit more guidance. I think plenty of people have drawn lines, but what I don't want you to do is connect 2 dots on this point, on this scatter plot. Because if you are connecting 2 dots, then you are only using 2 data points. And we are trying to use all the data points and find the line that fits all of them as best as possible. And so I'm going to draw my line of best fit. I'm not connecting 2 dots up here. I'm just going to try to draw a line that is as close as possible to all of these points. My line is going to look a little bit different than your line. There's my line. This is a very wishy-washy thing to do in a math class, because you're all going to get different answers to the same problem that is totally acceptable in this problem, okay? So there's my line of best fit, and now we'll move on to the next page. And just a little vocabulary, since the data in the scatter plot appear to be roughly linear, it's not a perfect straight line that hits all the points, but the points aren't distributed like, here's an example of something that definitely is not linear. Suppose that your data points were something like this. I would not say that a straight line is a good fit for that data. Maybe, maybe some kind of a curvy thing would be like a better fit for that data, and we will talk about curvy things like that later this semester. But the data points that we have are pretty darn close to all lying on the same line. It's not perfect. It's not going to be perfect when you have real world data, but they're pretty close. And so when it's pretty close, we say that the two variables, in this case t for time and p for percent, are approximately linearly related or linearly associated, just that they are close to a straight line. Okay, part A. Of all the lines that we could draw, and we have about a dozen different lines that we just drew, the best line, that's the one that's graphed above, has a name. We call the line graphed above the line of best fit for the data, or the least squares regression line, or more simply, just the regression line. So how do we find the actual line of best fit? Okay, so number one, I'm not going to ask you to do that in this class because we don't have the tools to do it. But if you really want to do it, you take a statistics class and you will learn exactly how to calculate the slope of the best line. At this moment, I'm not even defining what the word best means, right? This is really not a mathematically precise thing we are doing. But there is a mathematically precise definition for the best line, the single best line of all the lines we could draw. None of us drew it, including me, but there's a piece of software that I asked to draw it, and there it is. So, okay, so everything we do is just going to be approximating, so don't stress over that. Moving on, part B, we can use this line, the line that I have drawn on the top of this page, to make predictions about the data. We're going to use a line of best fit to predict the percentage of fatalities due to drunk driving in 1993. So coming back up here, 1993 corresponds to what value of t? Remember, 1980 is t equals 0. So this is 13. Yes, 1980 is our 0. So go to the graph, find the place where t equals 13, and then we're going to go to the line itself, the one that I drew, not the one that you drew. We'll go to t equals 13, which is here. We go up to the line, which is here. And how do we use this line to predict the percentage fatalities in that year? Where do I go from this point I found? We'll just go straight to the left, yeah? Take that guy, we went up that way, and now we're going to go straight to the left. And we're just going to read. I'll call it 43. If you said 42 or 44, no problem. Did we have data in the table for 1993? No, 1993 is not in the table. So we are getting new information. It's not perfect, it's not exact, but we didn't have an exact number anyway. So this is our best guess using the best fit line. I'll call it 43. Use a line to predict the percent, so we'll say about 43%. Okay, so that's how we use the line of best fit, just looking at it graphically. Again, lots of estimating, which means there's a range of full credit answers. Okay, so now we're going to do something even more precise. We are going to find the equation of that line right there. The equation of the line that's drawn, the best fit line. In order to find the equation, we need 2 points. So all we're going to do is find 2 points that are on the line. We're going to pick 2 points that are on that line. Now, are any of the data points on the line? Are any of the data points perfectly on that line? Not. And even if you have some data points that look like they're on the line, it's only because the data point is exaggerated in size, right? The data point is just this teeny tiny little dot that really we shouldn't even be able to see. So I just made them big so we can see it. So none of the data points are actually on the line, even if some of them are pretty darn close. So when we pick 2 points that are on this diagonal line, we are not picking data points. They aren't on the line. So all we're going to do is try to read off some points that look like they are easy to read. So I don't know which ones I labeled below, but that point right there looks like it's pretty close to being on the line, and it's something that I can read the exact coordinates of. So this one is 16 and 40. Is that one of the ones that I wrote? Right, so do you see how I found that? I'll erase it so we can see it. We are looking for points that are on that diagonal line where we can estimate the coordinates. We can read them off. So I'm going to pick this guy right here, which is close to 1640. It's not perfect. Again, there's latitude. You can pick a different point, but let's just all be consistent so we get the same, we can follow the same process here. What was the other one I said? 2035, can we find that? Does that seem reasonable? So right there. I can guarantee 2035 is not on that diagonal line, but it's pretty close. And I'm just looking for nice numbers that I can play with. Okay, and now that we have 2 points, and I say find the equation of the line connecting 2 points, well, this is equivalent to a problem you just did in the activities. What do we need to calculate first? Slope. And then once we have the slope, we find the y-intercept, and you go through the whole process just like you did. I think a lot of this is written out. Oh, it's not. We got some blank lines to fill in here. Okay, so let's fill in. Change in y over change in x is our normal equation for slope. But in this case, we don't have x and y. We have t and p. And part of what I'm trying to accomplish is to get us comfortable using letters that aren't just always x and y. So instead of change in y, what letter are we having? It's p, right? X is the t, y is the p. So this is now a change in p over change in t. That's good. And then we're going to subtract. Upstairs, I'm going to do 40 minus 35. That's that direction. You could choose the other way. Downstairs, what do I have to put now? 16 minus 20. That's good. All right, upstairs we've got a 5. Downstairs a -4. Normally you would just leave that as a slope, but in this case it says write your final answer as a decimal. So without a calculator, you guys know this one, right? Quarters involve 0.25s. -1.25, that's good. The other thing it says is include units. Oh, this is one of my favorite things about the smartboard, by the way. Did you see what happened when we crossed the yellow highlighter on top of the blue highlighter? You see what happened? What happened? Turned green, which is some, like, you know, technician, some computer programmer typing in something. Hey, if they do yellow on top of a blue, let's make it green. Okay, including units. What are the units? I don't know. Let's go back. The 40 and the 35. What were they measuring? Were they T's or P's? They were P's, which means they were in percent. So I guess this means it's 5. I'll put it here and then I'll move it over. 5% was the change there. -4 what? Years, right? The time was on the bottom, 16 years, 20 years. So that's years there. Makes sense on the fraction, but it's the same one over here even when it's a decimal. And so that's -1.25%. What do you want to change? What word can we change? It's per. That's how we always interpret slope. It's always make it per. Don't say divided by. So that's -1.25% per year. So what does that mean was happening with the percentage of fatalities due to drunk driving? It was going down by 1.25% per year. That's our sentence. We'll just write it here. More practice interpreting slopes is a good thing. The percent due to drunk driving decreased by 1.25% per year. Percent of the fatalities that were due to drunk driving. No, but I'm being a little bit lazy, but yeah, the percent of fatalities due to drunk driving decreased by 1.25% per year. Okay. Now, why didn't I write the negative in that number? Because it was negative 1.25. We wrote the word decrease. That absorbs the negative. Okay, again, this is an approximation of reality. Did it go down by exactly negative 1.25%? No, in fact, it wasn't a straight line, right? I mean, like we drew a straight line and my computer program made a straight line, but the dots are not on a straight line. So this is just our best approximation of reality. And it's something we can understand, down 1.25% per year. Okay, it's a simplification, but it's one that I can digest, as opposed to the complicated reality, which, you know, like is described by something way more complex. I mean, honestly, my computer program here could very easily find a nice curve that goes through all those points, but that's not going to be anything as useful as about 1.25% per year was the change. Right? Okay, so step 2 is here, find the equation of the line. All right, so we've got the slope. We've got 2 points. Again, this is like one of the problems on the activity we just did. So let's give it a shot. Normally, we'll start with y equals mx plus b. But like I said, part of my goal here today is to get it so we don't have to rely on exactly those letters every time. So we are changing the y to what letter? Is to p. Again, just go back up to our key here at the top of the screen. Y is p. So this becomes p equals m. X becomes t plus b. That's good. M times t. Okay, and now we'll do the process that you did several times in the activity. M changes to what number? Negative 1.25 t plus b. Great. And then we're going to find the b by changing the t and the p into some numbers. You have 2 points to choose from up here. It doesn't make any difference which one you use, but let's all pick the same one. Let's use the first one. So the p becomes what? Becomes 40. But it's really easy to call it a 16 because we're not in our familiar XY land. So just take your time. I think it's really important when you write up here t comma p, just put XY up above just to remind yourself of what it normally is. Okay, so p becomes, that's the second guy, that's 40, equals negative 1.25 times t becomes 16, same point, just choose the other coordinate, plus the b, which we are finding. Okay, we can scroll down a little bit. All right, this becomes 40 equals, okay, I think that's 20, right? Negative 20? It's b. Move that negative 20 over to find b. And we get b equals 60. So that means our final equation, copying it from here, p equals what? Trying to find b, so add this 20 to move it over to the other side. So p equals? That's good. That's the equation of our line. Any questions on that? Okay, just a quick reality check. If we had chosen not to plug in 1640, but to plug in 2035, same or different final answer? Same. You have 2 points, you pick either one. It'll look a little different in the intermediate steps, but at the end of the day, same. If we hadn't used the point 60 and 40, but had picked a different point up there, would we end up with the same or different? Different. The equation of the line is completely dependent on the points that you pick. And so when you take a quest or a test, I expect that we're going to have maybe 20 different answers here, and I can give 20 full credit solutions for 20 different answers, as long as they're all reasonable, okay? All right, next page. Okay, this is just us recopying, so we can use it here. Somebody remind me. Negative 1.25 plus 60, thank you. Okay, so there's our regression equation. That's just the fancy name for the line of best fit. And it says in this case, we can figure out how accurate we were when we picked, quote, nice points on the line, because we were just estimating the points that we picked were almost certainly not on the line. So according to GeoGebra, which is the name of the software that I use to create that graph, the line of best fit is this. There's more digits in those decimals, but I figure this is enough for our purposes. Again, in order to find the exact numbers, there's negative 1.19 and the other one statistics and or calculus. Like we just don't have the tools this semester to get the equation, but we can at least compare if I tell you what the equation is. So were we good? Yeah, negative 1.19, how far is that from what we said? 0.06, that feels pretty good to me. 58.6 compared to the 60, 1.4, 1.5, that seems okay to me as well. Okay, now we're going to use our regression line to predict the percentage of fatalities due to drunk driving in 1993. We actually answered this question already. Go back to the previous page. How did we answer this question before we had the line? What's that? It did go down each year, but how did we answer this 1993 question? Where is it? Part B on the previous page. How did we do this? We looked at the graph, and we went to 1993, and we went straight up, and then we estimated what we got when we went straight to the left. We're going to do better now, because now we know the equation, or at least something close to the equation of that line. Okay, so P equals, all right, let's try negative 1.25 times, I've said it before, but what is the value of T for 1993? 13, again, 1980 is the 0. So all we're doing is plugging 13 right in there for the T and doing this calculation. Is that 46.75? Somebody help me out. What do we get? What is it? 43.75. Yeah, plus 60 at the end. Okay, so 43.75. What did we say when we looked at the graph on the previous page? Yeah, something between 42 and 44. That agrees with what we put up here. Again, it's not going to be the exact answer. Okay, so in this case, 1993 was between known data points. Start of our data table was 1982, the end was 1999, and 1993 is squarely in between. And whenever you are using your regression line, that's what we just did here, to talk about a point that's between the beginning of the table and the end of the table, the word we use is interpolation. But we're about to see down here in bold the word extrapolation. What do you think we're going to use the regression line to find for extrapolation? Something that's outside, right? We've got the starting of the table and the ending of the table. And if you pick anything outside of that range, then you're extrapolating. Okay, let's try it. 2002. What is the T value here? Oh. Right. By that, 1980 is the beginning. This is 22 years later. So let's do the same thing we just did. P equals negative 1.25 times this brand new number of 22. And then plus the 60. $32.5. Somebody with a calculator? I'm going to be brave. What is it? Hey, 32.5. Good. And again, that is an example of extrapolation because 2002, even though it's past, is not in between our data points. Okay? Interpolation between, extrapolation outside. In terms of how confident we are in any of these estimates, we should be more confident when we are using data in between the given points, the interpolation example, than we are extrapolating, because for all we know, something dramatic changed after our last data point, right? 1999 is the last piece of info we had. Could be that something completely changed the game after 1999 and we don't see any evidence of it because our data table ended there, okay? So extrapolating is just riskier. It's not that it's a bad idea. Sometimes it's the only thing you can do, but it always comes with this kind of grain of salt caution. Hey, just be careful. It's outside of our data range, so something might have changed and the data might not be reflective of what's the current reality. Okay, I think that is that. So we have 12.5 minutes. See how far we can get on the activities, and we'll just pick up here next time. Raise a flag if I can help.